Today's notes are on key parts of a graph. And there's a lot of information packed into this lesson as well, so make sure you take your time, pause this when needed, look over everything, make sure you fully understand all parts. To get started, we're just going to quickly review end behavior from a graph. And end behavior was from the last lesson. End behavior is when you look at the specific ends of the graph and you determine whether they face up or down. So when we write end behavior, we typically start at 0 and we head towards positive infinity on the x-axis. And we want to know, is the graph facing up or is it facing down at this point? And hopefully you all recognize that the end of this graph is facing down. The first part of our end behavior would be as x approaches positive infinity, that's this part here, the function approaches negative infinity, that's this part here. Next, we look at starting at 0 as we approach negative infinity on the x-axis. Is the graph facing up or is it facing down? And you should recognize that the graph is facing up. So the second part of our end behavior says x approaches negative infinity as the function approaches positive infinity. The only part of end behavior that changes is this part here. It's just the ends of the graph. So with that said, moving on to number 2, both ends of this graph are facing down. So as x approaches positive infinity, the function is facing down or facing negative infinity. And as x approaches negative infinity, the function is still facing down, which is negative infinity. So that's end behavior from a graph. End behavior that approaches infinity from a function, so when you don't have a graph, you can tell this by the degree and the leading coefficient of a function. As a quick reminder, if we look at something basic, let's take a look at a basic function such as f of x is equal to 3x squared plus 6. In this function, this value of 3, that is called the leading coefficient. And I always abbreviate leading coefficient as LC, just to save me some time of writing. So leading coefficient is LC. This number right here is called the degree. And the degree is always the largest exponent. So knowing those two things, knowing what the leading coefficient and the degree is, will tell us what the end behavior is. First example, we care that we have a leading coefficient of 1 and a degree of 2. What we specifically care about is that the degree is an even number and that the leading coefficient is positive. So you have two choices. For degree, you have even or odd, and the leading coefficient, you have two choices, negative or positive. So if the degree is even, and if the leading coefficient is positive, that is all we need to know, then our end behavior tells us that both ends of the graph are going up. Both ends of the graph are heading towards positive infinity. Our next example, we have y is equal to negative x raised to the 4th power. This would technically be negative 1x raised to the 4th power. Our degree is a degree of 4, which is an even number. Oops. And our leading coefficient is negative 1, so it's a negative value. Whenever you have an even degree, negative leading coefficient, both ends of your graph are facing down or towards negative infinity. All right, this side of the graph that I just marked, or just drew a pink square around, these indicate that your function is an even function. Oops. So if the function is even, then both ends either face up or both ends face down. To repeat that, if you have an even function, even degree function, both ends face up or both ends face down. That leads us into odd degree functions. So odd degree functions would be when you have something like an exponent of 3. If you have an odd function and a positive leading coefficient, then as you head towards positive infinity, the graph heads up towards positive infinity, and as you head towards negative infinity, the graph heads down towards negative infinity. If you have an odd degree, a negative leading coefficient, then as your graph heads towards positive infinity, the graph is going to head down towards negative, and as your graph heads towards positive, your graph will head up towards positive. Okay, so for an odd degree functions, the ends face opposite directions. So one will head towards positive, one will head towards negative infinity, but always opposite directions. All right, unfortunately, actually fortunately for you guys, you don't have to memorize this table because this year's open notes, but in the past you would just have to memorize these. I do think it's still a good idea to memorize them so you can do it a little bit faster, but it will be open notes. For the first example, we have y is equal to negative 3 times x cubed plus 4 times x minus 6. So remember that we're looking for the degree and we're looking for the leading coefficient. In this case, the degree is 3. And we want to know, is the degree an even or an odd number? And 3 is an odd number. Next, we're looking for the leading coefficient, abbreviated LC. We want to know, is it positive or negative? And this is negative. The number is negative 3. So on your note sheet, you should just look above and notice that this matches the section of saying it's an odd degree and a negative leading coefficient. So that would be the bottom right corner of the chart we just went through. And that specifically matches the end behavior that says as x approaches positive infinity, the function is approaching negative infinity. And as x approaches negative infinity, the function is approaching positive infinity. And that's your answer. For number two is not in standard form, which we do need our function to be in standard form in order to tell your end behavior. But there is a trick to this. So whenever you have a function that is not in standard form, you only need the degree and the leading coefficient. So instead of multiplying this whole thing out, multiplying it into standard form, you're going to multiply the first term of every factor. Now, before I do that, we do have to recognize that we have one exponent of 2. So if you have an exponent of 2, that's telling you to use that factor twice. So I'm going to rewrite this as x times 2x plus 1, and because this exponent is 2, I'm actually going to write 2x plus 1 times 2x plus 1. We used this factor twice. And my last factor of x plus 4. So instead of multiplying every term, I am only going to multiply the first term of every factor. And when I do that, I end up with x times 2x times 2x times x. I just multiply the first term, or every term I highlighted in purple, which comes out to 4, because 2 times 2 is 4. 4 times x to the 4th. And of course, there's more to this function, but we don't care about the rest of it, because this right here gives us the first term. So it gives us the degree and the leading coefficient. So in this example, the degree is 4. We just found that by multiplying the first terms. That's an even number. And the leading coefficient is also 4, which is a positive number. Looking at the table above, this would be the top left corner. So as x approaches positive infinity, the function approaches positive infinity. And as x approaches negative infinity, the function is still approaching positive infinity. That means if we graph this function, it's going to have both ends of the graph facing up. Okay, I want you to take a moment and do the on your own section by yourself. These are both functions that need to be multiplied into standard form. But instead of multiplying all of the terms, just do what we did right here in number 2 and multiply the first factor of every term. Because this is a long video and it's a long note sheet, I'm going to save time and not write out my answers to the on your own section, but the answers are posted on my website under the note sheet. And next we're going to talk about how the graphs can tell us what we know about the degree of a function and whether or not the leading coefficient is positive or negative. So we're kind of working backwards here. We're using the graph to identify the end behavior, and then we're using the end behavior to identify the degree and the leading coefficient. So for number 1, I noticed that the end behavior is telling me as x approaches positive infinity, so as we move this way, the graph is facing down. So the function is facing negative infinity. And as x is approaching negative infinity, the graph is going up. So the function is approaching positive infinity. So now I want everyone to look back at the chart we went over for end behavior and recognize that this matches when your degree is odd and your leading coefficient is negative, and that would be the bottom left corner of the chart. So this specific end behavior only has one outcome, and the outcome is that the degree is odd and the leading coefficient is negative. And for number 2, both ends of this graph face down on number 2. So as x approaches positive infinity, the function is heading down or towards negative infinity. And as x approaches negative infinity, the function is heading down towards a negative infinity. This end behavior right here specifically corresponds with an even degree and a negative leading coefficient. It's the bottom left side of the chart. So number 1 corresponds with the bottom right side of the chart. Number 2 is the bottom left side of the chart. So understanding the degree of a function and what it tells us about the number of curves or the number of zeros that you're going to see. Let's focus on these examples I have pre-done for you, and let's talk about the number of zeros. So the first one, a linear function, which is a degree of 1. A degree of 1 appears to cross the x-axis one time, which if it's crossing the x-axis, that means it has a 0. This is called a real 0. So no matter where you move this line, say we move this line to over here, it's still crossing the x-axis one time. That line can never cross the x-axis more than one time. If the degree is 2, you can see that this crosses the x-axis twice, so we have 2 real zeros. However, I could slide this whole function down, and if I did that, and I slide this down to, let's say, right here, now my new blue curve is not crossing the x-axis at all. So you can manipulate a quadratic function to have no real zeros. The cubic function crosses the graph 3 times. This example does. And I could move this function around the graph so maybe it doesn't cross 3 times. Let's say we move it, let's slide it down and to the right. Now this graph is down to the right and it only intersects 1 time. But no matter what, because the graph heads in opposite directions, it's going to have to cross the x-axis at least once. A quartic function, degree of 4, can cross up to 4 times, or we could slide this whole function up and maybe it doesn't cross at all. So maximum 4, minimum 0 times. And lastly, a degree of 5. We can see this has 5 real zeros. However, we could manipulate this around the coordinate plane and maybe it will only intersect once. But because the graph heads in opposite directions, it will have to intersect at least 1 time. So if we were to have a class discussion about what we just observed in those 5 graphs, I'm hoping that you recognize that any even degree function, which my examples above are a degree of 2 and a degree of 4, even degree functions don't ever have to cross the x-axis, which could give you 0 zeros, or they could cross a maximum of whatever the degree is. So the rule tells you that if you have an even degree function, the minimum number of zeros is 0. Minimum number of real zeros is 0. It doesn't ever have to cross the x-axis, and you have no real zeros. So 0 or none. However, the maximum number of real zeros, that would be this one here, is going to be the same as the degree. For example, if we look at the 2 I circled, so degree 2 and degree 4, you can see that within within the degree 2, the graph crosses the x-axis twice, and degree 4, the graph crosses the x-axis 4 times. So that shows you that it's the maximum number of real zeros. However, if you're looking at an odd degree function has to cross the x-axis at least one time. That means the minimum number of real zeros has to be 1, and the maximum number of real zeros is going to be the same as the degree. So when the degree is 1, my graph only crossed 1 time. When the degree was 3, it crossed 3 times, and when it was 5, it crossed 5 times. So our general rule here tells us that the minimum number of real zeros for odd degree functions is 1. Oops, sorry about that. And the maximum number of real zeros is the same as the degree of the function. Okay, so remember these are specific to even or odd degree functions. If we take a look at my examples, it says determine the minimum and maximum number of real zeros. I am not asking you for the zeros here, I'm asking you specifically for the minimum and maximum number. And that has to do with the degree of the function. For number 1, the degree of this function is 7. We specifically need to know, is it even or is it odd? And 7 is an odd number. If we have an odd degree and the degree is 7, that would be this category. So the minimum number of real zeros is 1 and the maximum number of real zeros is 7 because it matches the degree. And those would be your answers. Okay, for number 2. Number 2 is not in standard form, so we need to write this in standard form. However, we only need the degree of the function, so we only need that first term. I'm going to start by expanding my exponent, writing this as negative 2x times x minus 6 times x plus 3 times x plus 3. And I'm going to multiply the first term of every factor. When I do that, I have negative 2x times x times x times x, which gives me my power function of negative 2x to the 4th. 4 is the degree of the function. That is an even degree. And an even degree says that the minimum number of real zeros is going to be 0. It doesn't actually have to cross the x-axis. And then the maximum number of real zeros is going to be the same as the exponent, which is 4. And that's your final answer. For the next example set, we're going to analyze the graphs and identify the number of real zeros for each function. I did make a little note on the note sheet here. It says consider the multiplicity of each zero. So that's bringing in some info from our last lesson. So I'm going to count how many times the graph crosses the x-axis. And right there, I see it crosses once. Then right here, be careful, this one bounces, comes up, touches, turns, comes back down. So it crosses, but this has a multiplicity of at least 2. Could be any number larger than 2 that's an even value, but I'm just going to say 2 because we're estimating right now. So multiplicity of 2. I have another 0 here, it crosses through, and I'm just labeling all my zeros. So I do have a note, I'll put it in here now, and that's for my double 0 there. It says because there is a 0 that turns at the related x-intercept, we know that there is a multiple 0. Make sure to include this in your answer. So if I count up my zeros, I have 1. This counts as 2, so 2, 3, 4, 5, 6, 7, 8. So I'm going to say real zeros on this example is 8. And pay attention to whether or not the graph crosses or touches at that 0. And then for number 2, very, very easy. This graph only crosses once. So we would say that the real zeros is 1. I'll put a note at the top of this. Count the number of times the graph crosses the x-axis, or count the number of x-intercepts. Next, we're going to talk about zeros and turning points of a function. All of these key parts are helping us move towards graphing, which we will do in the next video. So a turning point of a function. This is a point where the graph of the function changes from increasing to decreasing behavior or vice versa. So in other words, it's the place where the graph changes direction. A polynomial function of degree n being any number larger than 0, has at most n distinct real zeros and at most n minus 1 turning points. So what does this mean? Well, if we put this into perspective, we can look at this example right here. So the mathematical description says if the degree is n, then it has n distinct real zeros. If the degree is 6, that means it has 6 real zeros. It also says it has at most n minus 1 turning points. So once again, if the degree is 6, then it can have at most 1 less than that for turning points, which would be 5 turning points. And that's determined because it is 6 minus 1. 6 minus 1 equals 5. Okay, that's not telling you that it has 5 turning points. It's telling you that the maximum number of turning points that that function can have is 5. Okay, for the last example set, we are identifying the possible number of turning points. And I just made this note that says turning points is 1 less than the degree. Number 1 is x to the 7th minus 6x plus 4. The degree is clearly 7. So the number of turning points, or the maximum number of turning points, because remember it can be anything less, is 6. It would be 7 minus 1. And that's your answer. So the maximum number of turning points for number 1 is 6. one less than the degree. Number 2, we have negative 4x squared times x minus 2 minus 3x plus 5, of which we need to find the degree of the function. So I'm going to expand this, and I'm expanding and getting rid of my exponent of 2. So right here I had 4x squared. I replace that as 4x times x, just so I can easily see what each factor is. I multiply the first factor of every term, so every multiplied term, which gives me negative 4 times x times x times x times negative 3x. That gives me 12x to the fourth, I was going to say third, plus whatever else, but we don't care about that. Clearly gives us the degree of 4. 4 minus 1 is 3, so the maximum number of turning points is 3, and 3 is your final answer. Okay, for the last section, it says putting it all together. This is basically an on your own section, and it's putting everything together over the last couple of lessons that we learned about polynomial functions. So this year we're really going to stop at this lesson. Previously we have graphed the actual function, but it's going to be very difficult to do that through a video, and also with me not being able to physically watch you guys graph your graphs. It's hard to help when I can't see what you're doing. These are quite complex. So for that reason, we just ask that you know all the key parts, you know everything on this page, but we are not going to actually ask you to graph until next year in pre-calc. So the answer to this is on my website under the note sheet. So work on it by yourself, try to get through all the parts. It's different parts from the last 3 lessons, and then check your work against my answer key on my website.